Good afternoon, everyone. This is Sri Kumar from EDS Technologies. Today, we are going to present a webinar on DEP MeshWorks, that is Detroit Engineered Products. I would like to just give introduction on EDS Technologies first, and then DEP MeshWorks to start off the presentation. So, EDS Technologies has been there in the market for the last 25 years. And this is our silver jubilee year. We are the largest PLM and visual simulation providers in India, catering to multiple principles like Dassault Systems, SAP, then Human Solutions Inc., so and so. And EDS Technologies has headquarters in Bangalore with presence in 13 locations across India. And we provide complete range of solutions on Dassault Systems, Dassault platform, that is including the brands like CAE, Innovia, Simulia, Delmia. So these are the brands we provide solutions for. And also we are already working with the simulation market in India for close to 15 years. That is presenting Simulia solutions like Abacus, FESAFE, Eyesight, Tosca, and CST, and so on. So we have been provided, in fact, we catered to almost 1,500 active customers across India, and among which you can easily find more than 150 customers working exclusively on engineering simulation field. So today, like we are already providing high-end visual simulation solutions on Simulia Abacus. So we have a dedicated Simulia team who are certified professionals in this area, and we wanted to provide further, complete integrated CAE platform for Indian market and customers. To keep this in focus, we have tied up with DEP MeshWorks recently, and DEP MeshWorks, they have been there in the market for more than 2 decades, and they are well known in the market for pre and post processing, and also on CAD morphing, CAE parameterization, multidisciplinary optimization, and process automation. So these are the areas where we have tied up with DEP MeshWorks recently, and definitely with these tools in place, we are in a position to effectively provide a complete CAE simulation kit to the Indian market. So with this, I will introduction, I will hand over to Mr. Karthik and Gautaman, who are basically from DEP MeshWorks, to highlight the solutions on this.
Karthik?
Yeah, I can take over. I'm just waiting for the controls. Thank you, Sri Kumar, for the detailed introduction about and congratulations on the silver jubilee year for EDS, and it is such a privilege to associate with you. So we hope to add a lot of value to your solution suite and also to your end customers. So with that, I would like to proceed and share a couple of stuff from my side in terms of introducing Detroit Engineered Products to your team and also to your end customers. So if I could be made the presenter.
Yeah.
Sure. So as Sri Kumar pointed out, Detroit Engineered Products has been around for close to 2 decades or more. And as you can see on this slide, the organization was founded in 1998. And our solution is formulated across, as you can see in this clock diagram on the right-hand side, the engineering consulting solutions, product development, software development, talent acquisition. These are the four verticals of the organization, and we are proudly the creators of Meshworks platform, and we are the leaders in the area of CAE and CAD morphing, as Shri Kumar rightly mentioned in the introduction. So we have our office headquarters in Troy, Michigan, and we are also having offices in Japan, Korea, China. We have a couple of office locations in India, one in Bangalore too, and then we have distributor facilities in Europe, and we have office in California also. So that being the global spread of the organization, I would also like to share with you the brief list of customers. As Shri also mentioned, EDS caters to a large customer base, and this is the sort of a representative list of customers whom DEP we service globally across from Japan till the continental America. So this being said, we would get into the topic of the day, which is to introduce about Meshworks to you. Following is the agenda that we have today for your review. From the EDS solution suite, we are very much used to the PLM solution set, as well as the CAD solution set, as well as the solver solution set that Shri Kumar rightly mentioned. So DEP comes in exactly in that space which connects the solver PLM side of the platform with the solver side of the platform. So that is the connectivity that Meshworks brings to the table. So in this, I'm supported by my colleague Gautaman, who is going to demonstrate live what is Meshworks, what is its value addition for sheet metal kind of components that we deal with, what is our value proposition for complex plastic components that we deal with day in and day out. Also, we'll look at the powertrain side of things and how our tool sets really benefits the powertrain users. We will also pay brief attention to some of the complex parts, which is today being, even if it's an electric vehicle, we have complex disc brake components, we have complex components with related to battery frames, we have complex components with related to bumper foams. So they're all quite complex, and people look for hex mesh. So we also want to present you some of our benefits from the hexa meshing tools. We also want to present you some of the automated model assembly tools, which are very interesting, and it can save a lot of time as users. We also want to present a unique perspective for the post-processing, especially if you are a Simulia user. If you are trying to look at a results file with multiple load cases, how do we get a unified picture of the hotspots in one shot? And how do we use that for doing model changes? So we want to pay brief attention to that as well. So as I proceed to the next slide, this is about the Meshworks, but I would skip this, and just to focus on this platform is together with EDS, we both are looking forward to present this as a CAE platform, which can help you from model building to model integration, and also enable your CAE/CFD models to the level of multidisciplinary optimization also. As Shri Kumar rightly mentioned, from the EDS suite today, you are benefited with Tosca, which is doing phenomenal work in the area of topology optimization, to Simulia, which is the solver of choice for many of the nonlinear purposes. So Meshworks will come in very handy if you are trying to build design space for Tosca or a parametric model for Simulia. So that's exactly what we mean by calling it a multidisciplinary optimization front-end tool. And this will enable you to go all the way from automotive. If you're from an aerospace defense industry, you will still find it relevant. If you're from a heavy engineering background, there also you will find it relevant. If you are even from the biomedical or biomechanics, even then the entire tool set is very relevant, because Abacus or Simulia is a widely used tool set for hip implant, knee implant, and cardiovascular devices. You will also find it relevant if you are looking at shipping, as well as the energy, which is the oil and gas sector. And Meshworks is not a new kid on the block. Meshworks has been around for quite some time. We are the leaders in morphing fan element and CFD models and preparing them for optimization. Now, what has happened is, as Meshworks, the version 8 onwards, we have integrated all the CAD libraries so that we could right away take the model from CATIA, in the native format or as an IGS or a STL or a step format, bring it into Meshworks, do all the model building work, and then export it to Simulia or Tosca, depending on which is your solver platform. And then if you want to set it up as an optimization, you readily have the complete parametric library in Meshbox. You can parameterize your FECFD models and then get it ready for optimization. So, and also this Meshbox also provides you a process automation module also, where we need not have to be an expert in TCL, TK or Python. So a CAE user, as a CAE user, can create process automation for his entire standard operating procedure. So that's the value that DEP brings to table. And if you look at this pie chart, sort of this summarizes what are all the tool sets that we bring to the table to help you out in your CAE SOP. So we are looking at pre and post processing. We are looking at top of the line CAE CAD morphing tools. We are looking at process automation, enabling design automation, and also the most important, the parametric CAE technology, which helps you to study what if scenario very quick. So the other benefit of Meshworks, if you look at it, it can prepare models of different kinds, especially in this automotive context. If you look at it, interiors, exteriors, body structures, powertrain components, driveline components, all of it can be modeled as components, subsystems, and assembly, and also get them ready to run in Elastina or Nastran, Simulia. If it's a CFD, we could get it ready to run on Star CCM and Fluent. So you can essentially call it as a CAE platform for your model building exercise. And a brief attention to what are all the key differentiators, if I were to say, as the CA users, you have option of multiple model building platforms, and we do appreciate that. And what is the key differentiator from the Meshworks perspective is the models that you build in Meshworks are automatically parametric, like how we build in CAD. So models, so making a fillet radius change and all that becomes very easy. Integrated modeler, in the time that you take to build a durability model and a NVH model, you can actually you can start off with a durability model. At the same time, the NVH model is a derivative out of that, so you can derive one model out of the other very quickly. That's the power of integrated modeler. Almost saves you 50% of the time in terms of model building. An automated modeler is also very important to, like I mentioned, we don't have to be an expert in TCL, TK or a Python to create automation in pre-processing. Meshworks does it for you. And associate modeler is very powerful tool, where if you have an existing mesh and a new CAD, the mesh can be automatically updated to the new CAD. That's quite powerful, and these are the features that make Meshworks stand out and really help the CAE users. And we have a long history of partnership with Simulia, as well as with iSight and Tosca. So the users of Simulia are already getting benefit if they are also using Meshworks at certain locations. We already see some of the solution architectures where the models from KT are driven into Meshworks, and then a parametric mesh model from Meshworks is working with Simulia. And the value is a very tight workflow for you, which saves a lot of time, and the data goes in and goes out seamlessly. That is very important for you if you are looking at just a pure play engineering judgment based work, or if you are looking at an optimization based work. Even then, the either a Tosca workflow or an iSight workflow, Meshworks is there for you to handle the mesh models. So we have a completely built up multidisciplinary optimization architecture with Dassault Systems products. So this is also available. We have published several literature. We will be sharing that through EDS to any of you who want to access those literature. So it's a pretty versatile platform, since if you're having Kitty on one side and the Dassault solvers on the other side, Meshworks nicely packages in between and helps you take your CAD model and get them ready to run on these solvers. So this was the introduction that I wanted to present to you, and I would now share the stage to Gautaman, who is going to walk you through and mention to you the advantages of our mesh modeling tools, as you can see here, which is the bread butter honey in terms of the sheet metal modeling. And then subsequently we will also see how Meshworks really works on complex plastic models. It not only meshes them but also assigns the thickness and gets them to run readily on the solver. There are some examples that my colleague Gautaman is going to share with you. I'm just browsing through the screen just so that you get an idea of what we have in store. Similarly, he's going to also walk us through on the hex meshing as well as the tetra meshing related areas. One example for you of complex intersected geometry and how hexa meshing is done. This is not the typical hexa meshing that we are used to in other pre-processes. There's a unique way, and Gautaman is going to share with you that. Some of these things that can be done in few minutes, especially the intersected hex meshes. We're also going to share with you some of the model assembly tools, be it 1D model assembly as well as the 3D model assembly with contacts and pre-tensioning, which we are used to in Abacus. Also going to pay attention to automatic contact fixing tools, which is a very important requirement for Simulia users. We're going to pay brief attention to that. And then we are also going to see the hotspot extractor. This is another tool where even if you are running analysis with multiple load cases, and we have different hotspots at different locations from different load cases, Meshworks helps you to see a unified picture and identify all the hot locations in one shot. So this can help us to do the downstream parameterization or feature-based feature addition to make the geometry better and meet the requirements. So on a whole, this is what Meshworks saves up you. It saves close to 40% of your modeling time at the very least of it. And there are certain very powerful tools like integrated modeling, parametric, associative, and automated modeling, which is going to save a ton of time for the user. That is our key idea that we want to present through this webinar. So now, having said this, I would hand the control over back to my colleague Gautaman. And he will take the stage from there. Over to Gautaman.
Yeah, okay.
Thanks, Karthik, for the nice introduction. And today, now we are going to see the live demonstrations of all these examples. So first demo that what we are going to see is on the tetra meshing. And I'm just going to use this as an example. What you are seeing on the screen is a print engine block model. And I'm going into the interactive batch meshing, where all I do is select a component and select a mesh template, which is available in the installation location. And I have not done any kind of CAD preparation or CAD cleanup in this model. So just imported a solid dump data where the volume is closed for tetra meshing, and I started the tetra meshing process. So as the process is running, I would like to go to the other window where I've generated this tetra meshing, and I would like to explain what is actually happening in the model. So as you can see, the model based on the templates, the fields are nicely identified and organized into different collectors. And so I'm just going to open the measure control panels. And this is what the measure control panels is going to look like. It consists of all the necessary inputs like the mesh type, the target element size, etc. And we have the feature identification parameters where we identify tubes and apply a specific mesh conditions on these tubes, as well as create the washer zones if required by the user. And similarly, fillets, so user can add multiple rows. He can have the freedom to choose whether he can have go by number of rows of elements or caudal angle or caudal tolerance or element size, etc. And finally, we have holes and fillet lines for sheet metal components. And we have the edge suppression parameters, process control parameters, the quality parameters, which includes both 2D level as well as the 3D level. And finally, we have the tetra mesh parameters. And one interesting point here is the user can also choose a layered tetra mesh if required, even for casting components with variable thickness. The tool automatically identifies in the background where there is a uniform section and keeps the number of layers as specified by the user. So now that we have seen the template, I'll just walk you through some of the locations where you can see the three collectors, which is fillets, and then we have the tubes along with the washers as per the mesh template and the non-feature region. So the identification and the mesh application is done in the background based on the template. So probably I'll just give it a few more seconds for the process to complete. So here we are not doing any kind of CAD cleanup on the model in order to provide a good mesh flow or a good mesh quality. Everything is taken care in the background itself. So once the process is completed in this particular model, I will zoom on to certain locations and show that to you. So here the user can add multiple rows. So this is an interactive batch machine process. So wherein user can load an assembly model and choose a lot of components for a single template, which can be tetra meshing or sheet metal meshing, etc. This is also available as a batch mode, meaning that you can create a folder which is having different assemblies, and then just give this folder as an input so that you don't have to load the model in the background. And the cool feature is even if you have an assembly with a lot of sheet metal components and a lot of welds, sometimes the weld data also is there in the assembly. Even though you can just give it in the batch mode, the tool automatically identifies all these kind of sheet metal components and only meshes those parts. So now that we have completed the tetra meshing, so I just do a return. And now all the components are organized into a different collectors. So just let me do an auto color where you can see nicely the fillets, the tubes and the washers. And it's been quality correct as well. So you have both the 2D level and as well as the 3D level. So just hidden the skin. And if I zoom on to some of these locations where you can actually see some sleever surfaces, and all these sleever surfaces are corrected in the background itself so that all the elements are passing the quality criteria. And the next important point here is, as Karthik mentioned, once we do modeling in Meshworks, the model becomes parametric, meaning that now, let's say, after doing the post-processing, I want to improve the stresses in these regions. So naturally, I go to fillet radius change. And if you want to do any parameterization on these fillet radius change, it's very simple. We have standard parameters called as auto parameterization casting, which enables the user to just select the surfaces that he's interested in and provide a range of value and just create the parameter. So we have 4 standard types of parameters: fillet radius, tube diameter, rib height, and rib thickness. So in this case, let me just select a couple of surfaces where I would like to do the parameter and provide a range. In this case, it is going to be a percentage change. So it's going to be minus 20% to plus 20%. And just execute. It's just a simple selection and execution. And once the process is executed, the tool also nicely gives a feedback of what is the current radius of the fillet. In this case, it is given as 3 mm. And as we review this parameter, so let me link the parameter. So now the radius has been changed from 3 mm to 3.6 mm, and then I'm now reducing it. So all these changes are on the FE level. So this is the fillet radius change. And I would like to also show you another example where we are going to change the rib height thickness. So let's take, for example, we would like to improve the stiffness in these regions. and the user can just go into the rib height change parameter, select the surfaces that you would like to change, and provide a range. In this case, I'm going to provide minus 1.5 to 1.5, which is an absolute value, and just execute. So the tool intelligently in the background identifies all these kinds of features. Since we have done the meshing, the intelligence is stored in the file, and then it enables the user to quickly do all these kinds of changes. So let me go ahead and change the parameter. So this is the rib height thickness change. And similarly, we have other parameters which will enable you to create a parametric model quickly based on your post-processing results. And moving on to the next demo, I would like to show you the plastics meshing capability. So many of the time, we spend a lot of time in doing these kinds of plastics meshing. Simple plastics machines like door trim, hard trims, even though they look very simple, a lot of time has been spent on quality correction, feature capturing, and thickness assignment. And even we go to complicated plastics like front fascia, rear fascia, bumpers, exterior components, etc. So in Meshbox, it is a fully automated process wherein user can go into the auto midplane mesh generation, choose all these default steps, which is identifying the features, the midplane pairs, generating mesh, stitching all these features like doll houses, locators together, and then inserting these features onto the base mesh, do all the necessary mesh flow correction, quality corrections, and making sure that the output of this tool is exactly in the mid location. And we have inputs based on element size or identification of pairs and remesh quality, etc. So I've just selected the model and I'm just going to say execute. Since it's going to take a couple of minutes to complete the process, I would like to take you to the next window where the process is actually executed. So here it just takes like 3-4 minutes to complete this process, and here it has been completed. So ultimately, the output is going to be a mid mesh that is there, which has been completely stitched and flow corrected, quality corrected, etc. And as you can see, the tool nicely identifies all the kinds of features that are there in the CAD model and also preserves them when doing this kind of auto meshing. So in one shot, the user can expect a good auto mesh. There are also certain tools which will enable us to do a lot of manual work also, which is what I'm going to show as the next demo. So for example, in this model, what I've done is I've just executed the first 2 steps, which is primarily identifying the mid-surface mesh and generating a mesh. So all of them are not stitched together. Now, if the user wants to go through a manual route, let's say because of improper CAD data, certain areas are not stitched together, the user has the freedom to use all these nice tools to quickly complete this task. So in this example, we have a 4-junction rib wherein I can directly go into the junction-based stitching and select all the 4 edges in the model. And once the edges have been selected, you can just do a middle click and it gets stitched. And similarly, we have some 3-junction capabilities where the user can select all the 3 edges in the model and then just say stitch. So this is a kind of a manual route. The user, if he preserves to go to an automated, much automated route, that is also capable. That is also available in Meshbox. Here, I'm just going to select the entire model, and in this particular area, where there are a couple of junctions, and I'm going to give a tolerance and say identify junctions. So the tool nicely identifies automatically the 3-junction, 4 junctions, etc. And in one shot, we can select all these assemblies and then say stitch. So this is also possible. So the manual route as well as the automated route. So the output of this automated tool is going to have a very good very good effect, that is nicely preserves the features as well as the quality. And the second aspect is thickness assignment. And most of the time we spend thickness assignment in these kinds of ribs where we would require to have a layered kind of thickness assignment. So for that also we have a separate tool wherein user can go into the assign nodal thickness, and we have the rib thickness function. So I'm just going to select the master component, which is a mesh, and then the surface. And I'm going to use an option called as auto identify ribs, which will automatically identify the ribs in the model where we would require to have a kind of a layered thickness assignment, and then provide a maximum thickness, let's say go to 10, and calculate min and max. Based on the surface, it calculates the min and max thickness in the model, and we can provide an increment value of, let's say, 0.1 or 0.2 based on the customer requirements, and say agree group. And here I'm just going to give increment value of 0.1 mm. And so for every 0.1 mm change in thickness, the tool is going to create a new collector and assign them. So we do have assign mode wherein we can go with the regular, if the model is not having these many ribs, we can go with the auto thickness. If the model is having a lot of ribs, we can go with the rib thickness tool. And sometimes the customer is also asking for nodal thickness assignment, where all the thickness is being stored in the element card itself instead of creating new collectors. So that is also possible. So with these kinds of tools, we can expect a lot of efficiency. I think it's just going to take a couple of seconds more. And once the thickness is all regrouped, we can also check mode, which will give us a kind of visualization of what is the thickness in each area and whether the tool has nicely identified and recreated it or not. So here, as you can see, it's nicely created a layer kind of thickness in all the rib areas, saving a lot of time to the user. So this is the thickness assignment tool. And next one is we have the sheet metal component. So it is just a floor example where it is very similar to our tetra machine. So we can just quickly set up the interactive batch measure. Select the model and then choose a template. In this case, instead of going for the tetra mesh, we are going to generate a mid surface mesh and then do the meshing. So here I would like to create a 10 mm mesh and say execute. So this is actually a solid component. In the background, the tool identifies these as solid components, extracts the mid surface, meshes them, does all the quality correction, flow correction, and then also applies the respective properties for these components. So whenever you have an assembly of upper body or lower body and you want to do these kinds of machine activities, it can be done in a batch mode, just overnight or in 2 to 3 hours time frame, where the output is going to be a model which is good mesh with good mesh flow and properties are all assigned. So the suppression and the surface editing options, all the hard point propagation, everything is taken care in the mesh template level itself. So let's just give it a couple of seconds more and the process will be completed. So here also the user can utilize these kinds of features like holes. If the user wants to identify holes, create washers, or avoid certain holes or close out certain holes within some diameter, that is also possible. And fillet lines where he would like to create some nodes based on a range, and fillets where the user can choose number of layers or based on caudal angle or tolerance. So all this flexibility is given to the user, and this template can be saved and reused whenever we have a project of similar kind. So the process is now completed. So now, as you can see, if I do a refresh, we would have a mid-surface component. And meshed. The mid surface, the mesh is taking place in the mid surface, and the properties also has been assigned. Just to review, so the thickness has been assigned to the component. So this is on the sheet metal components, and next moving our demo to our hex meshing. So this is just a cut portion of a bumper foam, and this has a lot of junctions, and we are going to show you just one method that these kinds of components can be quickly modeled. So I've just done a mid-surface meshing using the previous example of auto mid-surface mesh. And then once this mesh is derived, we need to have something called as a core one mesh, where it's something, it is looking like a 3D model, which does not exactly matches the boundary, but it captures the internal volume. So I'm just going to give a 5 mm element size and generate this mesh. As you can see, it captures almost 80% of the internal volume, but it is not necessary that it has to capture all the features. So in this region, it is not captured all the features. Similarly, in these regions as well. In certain areas, it is also overlapping in these kinds of areas. So this is what we call as a core mesh, which ideally would need to capture 80% of the internal volume. So this file has been saved, which has been used in the subsequent next step. And the next step would be to mesh this kind of this local model, and the type of mesh or the quality criteria is not actually needed. So it can be a tetra mesh or even a tessellation mesh with no quality. In this case, I've just mixed mesh, and then I've organized all these components in order to capture the features. So, for example, I've organized this particular area wherein I would like to have the demarcation of the fillets in the mid location. So, with this as my input, I can directly go into the Cartesian expression panel and then select all the external components, provide an element size, and the pass1 file or the core file is what we have created in the previous step, and this is what I'm going to import now. I'm just going to import this file. As you can see, this was our file in the previous step, and with these inputs I'm just going to select the cavity and say execute. So we have our hex mesh. So I'm just going to hide the screen so that we can see our hex mesh. And wherever we have organized, you can see that nicely the mid node is being captured or aligned as per our requirement. And if I am to take a cross-section view, and this is going to be the output of our expression. So this is one of the methods where we can quickly generate expression for these kinds of models. Similarly, based on the models, we have developed numerous methods to quickly do these kinds of meshing activities. So far we have seen the capabilities of tetra, plastics, sheet metal and hex mesh, and now we will move on to the next one of connections. So the next one I would like to show the capabilities of both 1D bolt connections as well as 3D bolt connections. So here we have a model where the connection is not yet been established, and we have the model assembly tool wherein the bolt connection tool itself is in a very automated way, wherein all the requirement is to select the components where the connections has to be established, and then I'm going to select the unthreaded portion, which is this portion, and then provide a diameter range to identify the tubes. So the tool is now detecting the holes between this diameter range, and it also gives the user the freedom to select or deselect additional holes if required. Okay, so yeah. So here, since it is a solid connection, I would like to show the demo for only 2 locations in the interest of time. So I'm just going to deselect all these tubes. So only in these 2 locations we are going to generate a solid bolt. So here we can go into the defined bolt. We've already calculated the diameter. This is going to be an M6 bolt, and we can create a bolt with washer, without washer, based on the number of layers or element size and the mesh type, hexa mesh or tetra mesh. So once all this has been filled out, the user can just say accept, or if he already has a template, the CSV file can be modified to accommodate all these changes automatically. And here I'm also going to check on the pretension surface, wherein it creates automatically whenever the bolt has been created. So now I'm going to say preview. So whenever these kinds of 3D bolts are created, when we check on this pretension surface, the pretensions start as well as the contact between the shank and the tube, as well as the flange and the bottom portion of the bolt head is also created, which would save a lot of time. So if the user wants to go for a 1D bolt connection, it is instead of going into the solid bolt connection, the user can choose what is the type of connection that is required. So here an M6 bolt has been created with washer as per our requirement. And if I were to put everything in a transparency mode and show you the surfaces or the pretension surfaces. So this is the pretension surface that has been created automatically, as well as the regular contact surface between the shank, the tube, and the bolt head and the flange. So let me just do a reset. And the next demo that I would like to show is creation of 1D bolts as well. So let me get out of this transparency view and the bolt modeling tool. bolt connection tool, wherein instead of a solid connection, I'm going to choose a bolt connection with screw type. The inputs are all very similar. The 3D elements, the unthreaded portion, and then the holes to detect between a given range. And once the tool has been detected, just like our previous step, we can select or deselect the automatic identification area. And we can also change the configuration. So here, this is the area where the bolt needs to be created. And I'm going to select my kinematic coupling. Link element is going to still be my B31 configuration. And I'm going to choose an auto vector. And material alone, I'm going to give a default material and say preview. So these are all like standard parts. If you have an existing component where all the sliders and beams needs to be moved to, that is also possible. So I'm just going to say realize. So now all the holes has been created between a given range in one shot. And let me do a transparency view as well. This is on the bolt creation. So, so far we have seen meshing and modeling, and the next one and the most time-consuming part for us is going to be the model checker. That is, the model that we have built, is it matching our customer requirements? So typically, it takes more than a day in order to review whether the contact surfaces or the bolts, the beams has been assigned proper properties, all the components has been given proper material properties, etc. And in order to do this in an automated way, we have created a tool called as model checker. So here we have something called as a SOR sheet, wherein I'm just going into the SOR sheet, wherein all the inputs like what is the part number, what is going to be the material, what is going to be the property, and who is working on these kinds of models is being given as a SOR sheet. And this SOR sheet has been is the input for the model checker. And automatically the quality parameters, the bolt diameter, if we have a separate file, it has been taken care, and other parameters like the washer diameter, whether it is 1.5 times, 1.6 times, etc. How many washer layers should be there, and what is the contact penetration, min and max tolerance, and the contact pair check tolerance. All of them has been filled out. And once it's filled out, we can go and create a template. So here we have templates based on assembly, that is whether we are going to check for contact area, contact penetration, or specific load cases, or meshing, like material property assignment, RB3 weight factor, etc. So here I'm going to select all these parameters and provide a name.
Just trying to check how much time we have on the clock. Do we have another 5 minutes to go, or?
Yeah, we have another 10 minutes.
Sure, thank you. So, sorry, Gautam, to interrupt you.
No problem. And now, if you want, the user wants to edit the template, you can go here and edit the template. So I have already have a standard mount mobility check, and just now we have created the demo template. So I'm just going to select the demo template and say execute. So based on whatever the inputs that we are given and the SOR check sheet on the model, the tool is automatically going to check for all these kinds of issues that are going to be there in the model. For example, bolt diameter check, what it is going to do is whether the properties of the shanks is being assigned correctly or not. So it gives you a nice progress view also. Once it has been completed, we can get a temporary status data, wherein we can see that some of the bolt elements are failing, wherein it is actually an M8 bolt of diameter 6 but the section properties has been given as 10 mm for the B31 element. So like that, based on the SOR sheet, the tool nicely identifies all these kinds of issues, and then the next step would be is to review or fix. So this is going to take another 2 to 3 minutes time, and in interest of time I have already done the check wherein it is failing for most of the errors. So once this has been executed, the second step would be is to review and fix the data. So let's say, for example, I'm just going to put the model in transparency view and the bolt diameter check. So it's saying that there are some failures, and I'm just going to say review. And this will highlight whatever the locations that are actually failing. Yeah. So it is failing in a couple of locations. So these are a couple of locations where it is failing, which is marked as red in color. And we can either save it as a set or automatically fix it, taking the inputs from the XOR sheet. So now we are fixing the bolt diameter. And the second one is going to be the pretension, whether the pretension loads have been applied as per the SOR sheet or not. Similarly, contact pair, whether the master and slave surfaces have been properly generated, or in certain cases the master will be in some locations and the slave would have been in other locations. So now, yeah, it has been fixed automatically. Similarly, we can go for contact area, contact penetrations, etc. So when it comes to bolt pretension, it shows that in certain regions, which is highlighted in red, where the magnitude is not matching with the SOR sheet, and we can say fix failed. And the failure gets fixed. So model checker is a tool which can be used to save a lot of time for these kinds of model validation before submitting the run. So model checker, and the next one is going to be the hotspot extractor. So far we have seen everything in our pre-processing module, and in one window itself we have the meshing, modeling, morphing, as well as the post and graph. The next examples are going to be the hotspot extractor, wherein I can directly go into the post-processing module, and I've already plotted the stress components. And since today's demo is going to be predominantly on the hotspot extractor, and directly jumping into the utilities where we have the hotspot extractor. Here we have to choose the input file, output folder, and the ODB file. And here we can choose which are the steps we are interested in. And I'm going to be interested in all the steps. So step 1, step 2, step 3. So let's take first 3 steps in this example. And then I'm going to choose how many layers to exclude from the rigids. So 2 layers to exclude, and 1 layer we need to exclude near to the contact regions. And we are going to choose one versus stress, and the component is going to be this component, and the threshold stress limit is going to be, let's say, 150 megapascal. And based on these inputs, when we say execute, the tool nicely gives us a model with sets explaining which is the area that is failing for our threshold value, excluding all these kinds of regions, rigids and contacts. So let me go into the next model where I have already imported the file in the interest of time. So here the different color represents the area that is actually failing. So these are the areas that it is actually failing for different load cases. So here we have sets wherein let's say this is load step 1, and all these element sets are failing for load step 1. So if I do a show only, we can see that these are the regions that is actually failing for load step 1. Similarly, load step 2, load step 3, etc. So this will give us a nice idea based on the load step, which is the region that is failing. And once this has been generated, we can use our auto parameterization tool to do the necessary design changes as per the hotspot extractor result. So this is on the hotspot extractor, on the post processing. Yes. So that's it from my side, Karthik.
Thank you very much, Gautaman. Thank you for all the demonstration that included all the way from the mesh modeling tools of different types of meshes, sheet metal, plastics, and tetra meshing, auto parameterization, model assembly tools. I think this gives a good flavor to the attendees today on the variety of value that Meshworks brings to the table as a pre-processing and post-processing tool, and also bridging all the way from CATIA to Similia. It acts as a very viable bridge. So this is what we had to share with you today in this webinar. Please feel free to visit us at www.depusa.com on our website for more information. We really appreciate EDS for giving us the chance on their platform to talk about Meshworks. Thank you so much, Shri and the rest of the team at EDS. We really appreciate it.
Yeah,
So
Karthik, we can take up any question and answers now if the
sure,
audience has.
certainly,
I
yes.
would request the audience to type in the chat box or raise their hand. We can take up the question and answers. Any questions, please? Yeah. Yeah, Mr. Ajay, can you please tell your question?
Sure.
Hello. Yeah, Mr. Ajay, you can type in your question in the chat box. Okay, I would again request the attendees, if there are any questions, they can chat with us, or they can raise their hand. They can unmute and they can ask the questions to our panelists. Okay, there are no questions. So, any additional queries, you can write to us. You can write to us marketing@edstechnologies.com. For any questions you have, please do write to us. The mail ID is displayed on your screen, marketing at edstechnologies.com. Yeah.
Sure.
Thank you very much, Karthik and Gautam. With this, we strongly believe that DEP Meshworks will definitely complement the portfolio, Similia portfolio, what we already have, and we can definitely, get into the complete market with all these integrated CAE tools. Thank you very much.
Sure.
Thank you.
Thank you for having us on your platform. Thank you.
Thank you all attendees and participants. Thank you.
Yeah, thanks.
Thanks.